Welcome. Let's take a look at trying to understand what concavity is, what it represents, and how we might determine whether a function is concave up or concave down. So we have a function here. Our function is -2 minus x plus x squared. Now, a differentiable function on some interval I is said to be concave up if f prime is increasing. So f prime is increasing. That means that the derivative is increasing. That means that the slope of the tangent lines are increasing. And concave down if f prime is decreasing. So if the derivative of the function is decreasing, or the slope of the tangent lines is decreasing. If f prime is constant, then there is no concavity. Points where a function changes concavity are called inflection points. So in this animation we're going to look at, we're going to pay attention to the red line right here. The red line segment is tangent to the curve at the point P. You'll also notice there is a blue dashed line just to the right, and the blue dashed line is just to the right of P, and this is going to help us determine whether the derivative is increasing or decreasing. So let's go ahead and reset this. Let's start over at -5. So I'm going to start incrementing x, and we can see as the line segments move together, we can now see that they're starting to separate. And keep in mind that the slope of these line segments, or the derivative, is negative. And as these slopes of these line segments become more and more flat or closer to the horizontal, their slope is actually increasing because we're going from a more negative value to a less negative value. So let's continue on. And we can see how the slope of the blue line segment is less negative than the slope of the red line segment. Continuing, and now it's really clear. So the slope of the blue line segment, or f prime, at the point for the blue line segment is larger than the derivative at the point attached to the red line segment. Let's continue. See? F prime is getting bigger and bigger, or it is increasing. Now, let's go ahead and calculate the derivatives. So let's go back. So the first derivative at -5 is -11. That's the slope of the red line segment. Let's go ahead and increase. Notice that -11, now the slope of the red line, or the first derivative, is -9. The slope of the now is -7. So we've gone from -11 to -9 to -7 to -5, -3, -1. Now notice that our slope is positive. Continuing on. See how that first derivative is positive, is now increasing. Now, I don't know that you paid attention to this second line about the second derivative. So let's go through that one more time. And this time, let's attend to the second derivative of our function. So the second derivative at p is 2 at -4. At -3, the second derivative at p is -2. At -2, the second derivative is 2. Notice as I go around, the second derivative of this particular function is always 2. Now, so what did we say? We said that a function is said to be concave up if f prime is increasing. Well, what's the criteria for f prime to be increasing? That means the derivative of f prime, has to be positive. And what do we call the derivative of f prime? We call it f double prime, or the second derivative. So a function is said to be concave up if the first derivative is increasing, which means that the second derivative must be positive. So let's take a look at a second example. Here we have f of x is 24 over 12 plus x squared. And the process is the same here. You'll notice that while this shape appears to be a hill, if you will, or downward, this says that the function is concave up. So let's go ahead and step through this first. So what do you notice happening with the blue tangent line and the red? Okay, so let's go back and start again. So notice that the blue line, the slope of the blue line is greater than the slope of the red line. That means the derivative is increasing, which means the second derivative is positive, which means the function is concave up at this location. Now let's step. Notice that we still have the first derivative being increasing because the slope of the blue line segment is greater than the slope of the red. So f prime is still increasing. So our shape is still concave up. Our second derivative is still positive. Notice that still have that increasing first derivative. So second derivative still positive, still concave up. Now, notice that those line segments lie precisely on each other. And notice the second derivative is 0, and the first derivative is 0.35. So let's back up to -5. So watch my first derivative. It's 0.175, 244, 0.326, 0.375. But as soon as I take my next step, 0.375, now my slope of my blue line is below the red line. That means those slopes are decreasing. That means the derivative is decreasing. And for my derivative to be decreasing, that would mean that the second derivative is 0. And now the function is concave down because the derivative is decreasing. We continue around. It's very clear that the derivative is decreasing. The slope of the blue line segment is less than the slope of the red. Continuing around, we can still see the slope of the blue line segment is less than the slope of the red. And we get to this point, though, where they're identical, where our second derivative is 0. And when we step beyond that, notice that the slope of the blue line segment starts to be greater than the slope of the red line segment, meaning our derivative is now starting to increase. And then we continue around. So let's start from the beginning one last time. So our first derivative is increasing. We've got 0.244, 0.326, 0.375. Our first derivative increased to 0.375. However, now our first derivative starts to decrease. We've got 0.284, 0, negative 0.284. Notice the decrease, negative 0.375. And now our first derivative will start to increase again. And we can see negative 0.375, negative 0.326, negative 0.244. See, we're increasing our first derivative. So in conclusion, we say that our function is concave up when f prime is increasing. That's equivalent to saying the second derivative is positive. And concave down when f prime is decreasing. That's equivalent to saying that f double prime is negative. Also, points of inflection are locations where the concavity changes. We saw a change here on the left side of our graph, and we saw a change here on the right side of our graph. I hope you find this helpful.